think they're just gonna hear it.
Good evening and welcome to the Minetti Shrimp Museum. My name is Julia Walters and I'm a Visitor Services student staffer. Before we begin tonight's program, we should take a moment to acknowledge the land on which UC Davis sits. For thousands of years, this land has been the home of the Patwin people. Today, there are 3 federally recognized Patwin tribes: Kachil-Dihi, Band of Wintun, Indians of the Calusa Indian Community, Quetzal-Dihi, Wintun Nation, and Yocha-Dihi, Wintun Nation.
The Patwin people have remained committed to the stewardship of this land for many centuries. It has been cherished and protected as elders have instructed the younger generations. We are honored and grateful to be here today on their traditional lands. Thank you.
Thank you.
Okay, everybody, welcome. Hope you can hear me fine. I'm David Britt from chemistry, and I'm the Winston co-chair, which has been very exciting. So, very excited to have our event today with Sarah talking about the origin of the Earth-Moon system. It's been a while since we've had one of these. In fact, I think the last one was the one when I was brought in as the co-chair. And a lot's happened in the last couple of years, as you know. Obviously, the reason we haven't had one in a while was we were waiting for being able to do one in person with the COVID restrictions, which has at least improved. Another thing that happened was we lost Winston Co. to a tragic accident a couple of years ago. It's very sad. So I think he'd be very fascinated to hear Sarah's talk today for sure. So. But then good things happen too. So we have a new dean. So I'm going to introduce Dean Estela Actequana, and she's the dean of the Full Letters and Sciences College. It's a pretty big job, isn't it? Yeah. So Estela grew up in the Republic of Cameroon. She came to the U.S. to study at Howard University, where she got a bachelor's and a master's degree in geology. Then she did her PhD in biophysics at Dalhousie in Canada, and then she went on the faculty circuit. She's actually moved several times, usually to higher and higher administrative positions. So, for example, she was head of the Boone Pickens School of Geology at Oklahoma State, and most recently, before Davis, she was dean of the University of Delaware College of Earth, Ocean, and Environment. And then we were fortunate in August 2021 to hire her here at Davis as dean. She's a noted biophysicist and same department as Sarah. So, Dean Actequana. Let's see, I'll leave that on. I don't know if that needs.
So thank you so much for that introduction, and hello everyone. I am really pleased to be here to welcome you in person, and of course those that are joining us virtually for the 3rd Winston Co. Public Lecture, which is presented by our college's Department of Chemistry. As Dave says, my name is Estela Actequana, and I am the Dean of the College of Letters and Science, and I joined the college in August of 2021. So I'm really excited to be here to connect with everybody here in person. It's really good to be back in person. It's not the same as being on Zoom. So thank you everyone for joining us this afternoon. I'm really excited to introduce today's speaker, who happens to be my colleague in the Earth and Planetary Sciences Department, Professor Sarah Stewart, who is really one of 3 faculty members in the College of Letters and Science who's been honored with the MacArthur Genius Award. She is a real genius, let me say that. But what is also really amazing about her is that she's an exceptional teacher in the classroom. I was passing by the design building and I heard her teaching, and I had to stop and listen. It was really amazing. So for me, as a dean, it is such a pleasure when I find faculty that do such phenomenal work in their research also pay the same attention to their classroom teaching for our students. So her research combines real-world experiments and computational models to explore how planets form. really fascinating work. Now, because I am also a geophysicist, I have some personal experience in this area, not the kind of experiment that she does, that's beyond my intellect. But in any case, in my field as a geophysicist, scientists use small explosions to create sound waves that give us beautiful pictures and images of the Earth. But Professor Stewart's research involves actual cannons, believe it or not, to recreate the immense forces that occur when planets collide. They're actually located next to the physics building not very far from here. In fact, her shock wave laboratory is one of very few in the world that is really dedicated to doing this kind of work, studying the properties of rocks and minerals under conditions of extreme temperatures and pressures. So if you haven't had a chance to see it, I'm inviting you to do so. Hopefully you accept visitors. The experimental results from our research are extremely important for creating accurate models of planetary collisions. With this approach, Professor Stewart has proposed a new twist on the formation of the moon. I really look forward to hearing about that today. But before I finish, I also want to tell you a little bit about my predecessor, the late Winston Cole. He provided more than 40 years of service and leadership to UC Davis and the College of Letters and Science, including 2 terms as dean. No comments about that. And as a professor of physics, he was an energetic and passionate advocate for education in mathematical and physical sciences, which he believed provided a fundamental background for a variety of careers. With his wife, Katie Cole, Winston endowed a professorship and public lecture series before his tragic and unexpected death in 2019. Dave Britt, who introduced me, distinguished professor of chemistry, now holds the Winston Cole Professorship in Science Leadership. We are so grateful to the Cole family for their generous gift to our college. And with that, I will turn the program over to Professor Britt. And thank you so much. And I hope you enjoy the lecture.
Okay, well, the dean told us a lot about Sarah, so I have just a couple of factoids and then we'll get going. So Sarah got her bachelor's degree at Harvard and then in some geosciences, and then went to Caltech and got her PhD in planetary sciences. And after a postdoc at the Carnegie Institution of Washington, she started back at Harvard as an assistant professor and in 2003. And then Dean Navratsky, who you'll see a picture of in a second, was able to move her to UC Davis in 2014, which is very exciting. She's won many, many awards. Just trust me, many, many awards. We want to hear about the moon and the Earth. But, and I really think, again, this is exactly the sort of talk Winston would like for this public lectureship, so we're all very excited to hear about this new creation story. So, Sarah.
So this is my first in-person lecture since the pandemic started, and I am so excited, honored, and a little nervous to be in person again. And I want to start by thanking Winston and Katie for establishing this professorship and the public lecture. As we gather back in person, it's so important for us to celebrate the joys of our scholarship at UC Davis. And this public lecture series is one of the key things that we can do for our community and to share with each other all of our wonderful work. So thank you for coming. You know, look at your neighbors and thank them for coming, and thank the online audience for joining in. You know, this is a positive thing we've learned how to do to extend our reach to people who are far away to participate in learning about the great work that we're doing at UC Davis. I am going to tell you a story today that we all share in wonderment. Each of us has had the experience of looking up and gazing at the moon and asking the question, why? Why is the moon in the sky? And every culture and every tribe has answered this question with their own stories. And these stories bind the community together, and they serve a purpose to explain the natural world around us. I'm a scientist and I tell stories. I try to transform my equations and experiments into narratives. Narratives that nourish everyone's curiosity about what they see around them, and narratives that bring you with me to the precipice of the edge of our established knowledge. And so today, I will tell the story about the origin of our celestial partner, and its story is also the origin of our home world. Our moon has several unusual characteristics. It is extremely large compared to the size of our planet. It's much larger compared to the planet than any other satellite system in our solar system. It has a tiny iron core, much smaller than the rocky planets that inhabit the inner solar system. It has a chemical composition that looks like Earth's mantle without the materials that boil at low temperatures like water and sodium. And so we know that the moon is linked to the Earth, but all of the scientists' stories that existed before the Apollo missions to the moon turned out to be refuted by the data collected by the astronauts and that we examined from the rocks returned from the moon. And so planetary scientists had to go back to the drawing board. And in the aftermath of rethinking the origin of the moon, the rocks brought back by the astronauts provided a key piece of information. They provided evidence that the moon had a global magma ocean, a key fact that wasn't established until we had the rock samples in hand. And with this key piece of information of the high temperature origin of the moon emerged a much more exciting version of the origin of the moon. So the giant impact hypothesis did not emerge until after the Apollo missions, and it was thought of by modelers and people who studied impact cratering as a scaled up version of many impacts launching debris into orbit, but settling into the idea of a single large event. And this is the story that scientists have been telling ever since the Apollo mission. Another protoplanet in the inner solar system, one that we have named Theia, struck the not fully grown Earth. The impact ejected material into orbit, forming a disk around the Earth, and the moon grew from that material in orbit. Now, cartoons do not do this process justice. And so luckily we have cinematic versions of the calculations of this event. And so here is a rendering of computer code calculation done by Robin Canup of Mars mass impactor onto about a 90% grown early Earth. And it gives you a sense of the extreme energies involved. The power of such an event, the energy per unit time of this giant impact, is similar to the power coming out of the sun at every second. And so there's enough energy to melt and partially vaporize both of the bodies. And so the Earth here has been transformed into a magma ball with a rock vapor atmosphere. And most of the material in the disk are magma blobs and moonlets. And in this grazing impact, the impactor suffers an initial collision and then returns for a second collision that ends up providing the torque to raise most of the mass into a disk around the Earth. And it is from this magma and vapor disk that the moon grows on timescales that are uncertain today, years to hundreds of years, depending upon the details. And this event is our standard reference model for the origin of the moon. Now, the accretion of the moon takes longer than our computer code calculations can calculate with fidelity. And so that stage of what happens next after the formation of this disk is usually calculated in separate models. And giant impacts are an expected stage in all planet formation scenarios. And so in our solar system and in the exodisks that we see around other stars and in the histories of the exoplanetary systems that we observe, we think that giant impacts were a phase that occurred in all of these systems. Now, giant impacts are quite diverse events because you can have different mass bodies impacting at different angles, at different velocities. They may graze and merge together, as this example showed, or hit and run, or be catastrophic and blow off the entire mantle in simulations that try and mimic the formation of the large core of Mercury. And so no two events are exactly alike. And so when the giant impact model was proposed, we took observations that we have today of the Earth-Moon system and tried to determine which type of giant impact, what combination of bodies could produce the system that we have today. And so the constraints that we were using, that we were trying to match with these models, were the present masses of the two bodies, the small composition, the small amount of the iron core, so we want most of the iron in the system to end up in the Earth. The magma ocean told us that the moon formed hot, and a key constraint on the outcome was the total angular momentum of the Earth-Moon system. Angular momentum is a conserved quantity, and so going back in time, as the moon, if you wind the moon's orbit back to where it formed, the Earth's day was very short, about a 5-hour day. And over time, as the moon migrated outward to conserve angular momentum in the system, the Earth's day extended to its present 24 hours. And so the combination of parameters that could achieve what we see today is this standard model for the giant impact, which is about a Mars mass body striking the Earth at a grazing angle at a relatively low velocity near the escape velocity of the two bodies. However, the drama of this story is that almost from the beginning, we knew there were problems with the idea of the giant impact. And the problems had to do with the composition of the body, its large mass, and the inclination of the lunar orbit. The moon's orbit is inclined about 5 degrees from the ecliptic plane defined by the sun. If it were at 0, we would have total eclipses every month, but we don't because the moon is oscillating up and down in its inclined orbit. In a standard giant impact event, we would expect the moon to actually evolve into the ecliptic, and so it's a puzzle. Why is the moon's orbit inclined? It is difficult to put as much mass as we see in our moon into orbit, and so all of these simulations either just barely make it or fall a bit short. And so there is still a difficulty in making the large mass of the moon that we have. And the most difficult problem for the physicists to match is the one of the nearly identical isotopes that we see between the Earth and the moon. And the isotopes I'm talking about are the stable isotopes of oxygen, titanium, potassium, that are all very similar between the Earth and the moon. But what we've learned from meteorites is that most planetary bodies have a unique set of isotopic ratios of stable elements, and that these isotopes can be used like fingerprints. So I can group meteorites that came from Mars. I can group meteorites that came from Vesta by their unique isotopic thumbprints. It turns out from the Apollo samples that the moon has almost an identical thumbprint to the Earth. But the computer simulations that matched all of those constraints found that most of the disk around of the Earth was made out of Theia, this other planet in the inner solar system that should have had its own isotopic thumbprint. And so the prediction is that the moon should actually be different than the Earth, but it's nearly identical. And when I was beginning my career as an assistant professor, there were great debates about this particular problem, to the point where I had many colleagues who actually were arguing to us impact scientists that we should reject the idea of the impact origin of the moon, go back to the drawing board, and satisfy the chemical observations. And if we could have, we would have. However, those Apollo data had ruled out any other viable option for the origin of the moon, and there was no option B left to turn to in trying to explain the generation of our moon. And so what transpired next was for the community to focus on variations on a giant impact model. Is there something that we can change, some restriction that we can relax in order to explain our observations with the moon? And these variations have been everything. Maybe the Earth started molten, and by the fact that it was a liquid body instead of a solid body, did that generate more material from the Earth into the disk? Instead of a single giant impact, could we have had many smaller impacts that made many moons that then formed into our own moon? Instead of having an impact that merged the two bodies, was it an impact that was a hit and run? Was there already angular momentum in the system that we could have used? Did the system have greater angular momentum in the past? These are all variations on the basic giant impact model. And one by one, no one is completely satisfied by any of them. They either have what one could consider special pleading constraints upon them, or bring up other problems that are harder to solve than the original problem, and we are in a situation where tweaking around the problem doesn't seem like a very satisfactory solution. In the middle of these debates, and you must appreciate that scientists love debate. And so in the middle of these energetic debates, my graduate student and I had a Eureka moment. So this is Simon Locke, whose thesis work was the main thrust of our idea for the origin of the moon. We had a Eureka moment sitting and looking at the code outputs together, where we realized that we had made a mistake. That something we had assumed to be true about giant impacts was not true. And that this assumption had made the whole community interpret the outcome of these computational calculations incorrectly. And to that day, where we realized that something different had happened, we actually didn't understand what was going on at all. We just knew that our assumption was wrong. And in order to understand what was happening, we had to relearn something we thought we already knew. And the thing we had to relearn was the answer to this question. Now, this should not be a complicated question, but many of you remember what happened to Pluto. We had a little problem of the number of planets in the solar system changing every year as astronomers kept finding more and more large bodies in the outer solar system. And this raised something of a conundrum in the community, a big enough conundrum that the International Astronomical Union, a collaboration of scientists, decided to define formal definition for planets. What is a planet? And so There are 3 criteria that formally define a planet. Do you know what they are? One, she's shaking head. It's a sphere, which means the body is in hydrostatic equilibrium. Both the Earth and the Moon are spheroidal bodies and satisfy that criteria. But the Moon is not a planet because it doesn't orbit the sun, it orbits the Earth. And so a planet orbits our sun. If a planet orbits a different star, we call it an exoplanet. Okay? And then the third criteria is what demoted Pluto. It has too many neighbors. And so it's an arbitrary constraint, but it generated two classes of planets. Formal planets that orbit the sun, have cleared its neighborhood and are spherical objects whose shape is defined by hydrostatic equilibrium. And the bodies that did not clear their zone in the solar system are called dwarf planets. So Pluto is a dwarf planet, Ceres is a dwarf planet, it has a rounded shape, and there are several other bodies in the outer solar system in the neighborhood of Pluto that also have rounded shapes that are dwarf planets. And so this is a reasonable definition of planets, and it distinguishes planets from smaller, colder bodies that don't have hydrostatic shapes. So hydrostatic shapes are dominated by the gravitational field on the body, but smaller bodies that are colder and less massive have strong materials, rocks with shear strength to them, and too low of a self-gravitational force to deform that rock into a hydrostatic spheroidal shape. And so these are not defined by gravitational equipotentials, they're defined by the strength of the rock, and they look like potatoes. These are the bodies we visited up close, asteroids and comets, with their oddball shapes. And so this was very well understood. What was not understood was the question we were just beginning to answer the day we had our Eureka Moment, was what happens when a planet gets really hot? Okay, so it's the other end of the spectrum. And no one had actually asked this question. And so we were able to try to answer it because we were working in the lab on understanding what happened to planetary materials when they get really hot, because we do shockwave experiments that can drive materials to huge energy densities at high pressures and temperatures, and we can measure what the state of that material is. And so when we construct a computer model, we can have greater belief in the fidelity of that model. And these experiments are done on national platforms like nearby Livermore National Lab at their National Ignition Facility, which recently is on the threshold of fusion. The Sandia Z machine is a huge capacitor that discharges a current pulse that can be used to launch centimeter-sized aluminum plates to 40 kilometers per second. It's almost the orbital velocity of the Earth around the sun. There are other laser systems, and in smaller systems like my gas gun lab on campus can reach all of the pressures of planet formation. All of the pressures and temperatures of planet formation are now accessible to us in the lab, and so in these giant impacts, you can think of each experiment as following a small parcel of material through that process, compressed to high pressures and then released again. And then one by one, through many experiments, we build up our models of the materials and use these models in the codes to understand what happens in a giant impact. And so in experiments that we call shock thermodynamics experiments, we can gather this data, and so our experiments are normally on small pieces of minerals and rocks, where we send planar shock waves through them and measure the densities, pressures, and temperatures that are achieved. And these experiments are an intensive amount of work to build, and my lab was described as having cannons. It has 2 cannons. Here is an example of one of them. You use in an experiment. Watch the little pin at the end. That's it. If you hear any more than that, something went wrong. Okay? And so at the other end, so we use gunpowder and compressed gas to drive the little metal plate to several kilometers per second, we can generate pressures millions of times greater than the surface pressure on the Earth and reach most of the conditions within the interior of the Earth. And to get to higher pressures, we use these other national facilities like the big lasers and the Sandia Z machine. And so our targets are instrumented. The experiments last hundreds of microseconds to several microseconds. On the big platforms, they can last tens of nanoseconds. So the data are collected in real time, and afterwards everything is destroyed in these big experiments, and you literally vacuum out the debris. And so with this information that we gather, we develop improved material models to use in codes that are basically calculating gravitational forces coupled with these material models that describe the relationships between pressure, density, and the internal energies of the iron cores and rocky mantles of the colliding bodies. And with that information, we can calculate the shape and size of bodies after a giant impact, because we can now use our understanding of how energy changes the shape of a body in order to predict what will happen. And so the picture that we had in our head was like this rendering where there was a hot planet in the middle with a rock vapor atmosphere and a disk orbiting around it. It was really the evolution of that disk that was key to understanding the origin of the moon. But what we learned was that the object in the middle actually was not a planet and was something else. And it took us a while to actually be able to explain that. And so the definition for hydrostatic equilibrium is given by this equation. On the left is basically pressure gradient forces within the body, and then balancing that with gravitational forces and rotational forces. And so with a spinning object, as you make it spin faster, the sphere will turn into an oblate spheroid where the equator is greater than, the equatorial radius is larger than the polar radius. So this is an example of a fast spinning Earth mass planet that we've calculated using these models. And in this case, the planet is cold enough to satisfy this equation, and there is a static state that where the shape of the planet does not change with time. However, when one makes the planet hotter, this is what happens. The same mass, but now just raising the internal energy of the planet makes the equator so large by the expansion of the material that the equatorial radius meets the same radius of a co-rotating orbit, a synchronous orbit. And in that case, the equator, which is a function of the mass of the body, how hot the body is, how fast it's spinning, that equatorial radius exceeds the location for synchronous orbit. And part of the planet basically cannot rotate together with the core of the body. And instead, it sort of squishes into a disk. And as you keep increasing the energy, that disk becomes more and more massive. This body is not static. It does not have a fixed shape with time, and instead, over time, that disk will keep spreading, and it is now an object that we call hydrodynamic. And so it violates the definition of a planet, and we then were obligated to name it so that it could be described as a new type of astronomical object, and we gave it the name synestia, which was based on the goddess Hestia, the goddess of the hearth and home, and sin because we wanted to emphasize this intimate connection of material between the inner part of the body and the outer part of the body. And so instead of thinking of a planet with a disk around it, we instead have an object that is just so hot that part of the mass is now extended into a disk, and it's in this different system that the moon must form. And so our definition space of planets has a cold limit, where bodies are small enough, cold enough to not be rounded in their shapes, and a hot limit, where a planet's size is so great that it extends beyond the limit of co-rotation and forms this dynamic structure that we call a synestia. Now, most giant impacts make synestias. It turns out that the energetics of the giant impact phase of planet formation will make synestias. Here's an example of a synestia forming impact that has an initial angular momentum by a fast rotation of the planet before the impact. The impact has a greater kinetic energy compared to the canonical moon-forming impact. And what you'll notice is the outer layers are not dominated by magma blobs, but instead are dominated by rock vapor. The outer portions are almost completely vaporized. The central mass is extended to the point where it violates the definition of a planet, and this is a synestia. And when you just look at the parameter space for giant impacts, this is a common outcome. And so in our solar system, the Earth could have been transformed into a synestia multiple times by different giant impacts, and then cooled in between, where the rock vapor condenses and turns back into a planet. And similarly, we expect exoplanets to also have achieved this same state of being a synestia and then cooled again. And so within this structure, the moon would form. Synestias today are a theoretical object. So in the time since we first proposed it, they have stood the tests, and this is a robust prediction. It would be possible to observe a synestia should we be lucky enough to be looking in the right place in the right time. And it is something that astronomers are looking for, just as they are looking for more exoplanets, but we haven't observed one yet to date. And so they are today a product of our scientific imagination and calculations. And this synestia is a temporary object in our solar system because the rock vapor will cool at our distance from the sun and recondense back down into an object that looks like the Earth. Within this system, this puffy rock vapor with a composition of the bulk silicate Earth, our moon will form. And this is a different chemical environment for the origin of the moon compared to the previous versions of the giant impact. And in this environment, you have to imagine torrential magma rain. So we had a torrential storm just a couple days ago. Imagine a magma rain version of that storm. As this synestia cools, there will be torrential rain at a rate greater than the strongest hurricane rainfalls on Earth. And that those magma droplets will fall into the synestia structure. Some of it will become revaporized, some of it will be incorporated into growing moonlets and grow into moons within this system. And the chemistry of that moon will be dominated by equilibration with that rock vapor around the growing moonlets. And so what is different about an origin within the synestia is that the synestia has a lot of rock vapor pressure. Pressures at tens of bars compared to negligible vapor around the moon in the standard model. And so this is a system that we can calculate the predicted chemistry of the moon in this system. Basically, if you take the elements that we observe in the moon and the Earth and order them, in this case, by increasing volatility, we can normalize the moon to the bulk silicate Earth. And the moon has this overall spider pattern, but generally depleted in materials that are more volatile, that would vaporize first. And then we calculated the composition of the moon, assuming that the moon formed under different pressures. And what we find is that the moon forming at low pressures and at temperatures controlled by the boiling point of rock vapor, of magma, that moons that form surrounded by very little rock vapor do not reproduce the observed chemistry, but surrounded by tens of bars of rock vapor, like the red line, 20 bars, provides a much better match to what we see in the moon. And this was the first quantitative match to the chemistry of the moon using the synestia model. Now, in this case, so this was a rah-rah moment as a very satisfactory outcome after realizing that there was this very different environment that the moon could have formed in. Now, since this work, we are now trying to do much more sophisticated chemistry calculations. Calculations that can tell the difference between the stoichiometry of the materials at the deep interiors of the structure out to the vapor around the growing moonlet and the composition of the moonlet. And so the way forward in testing this model is to look at more detailed predictions in the chemistry and isotopes between the Earth and the moon. And so this is the current status of the field as our current development of these techniques. And so what I want you to walk away with in terms of what should you carry around in your head, what should you tell your family at Thanksgiving, is the new idea on the origin of the moon, is to have in your head this idea of a synestia, which is what happens when a planet is so hot that it can't rotate altogether, torrential magma rain, and within this synestia, the growth of a magma moon. As the system cools by radiating into space, the size of that synestia will shrink as the rock vapor condenses out. But the moon remains in orbit, and so you can imagine that the rock vapor shrinks and shrinks until the point that the moon is now outside of the condensing body that will turn back into the Earth. At the time that this separation happens, the body is still a synestia, and it has to cool and cool and cool before it turns back into the Earth. And so if you're a Star Trek fan, there's the movie where Star Trek emerges from Titan's atmosphere, and you can think of the moon emerging from the synestia atmosphere as imagery of the origin of the moon and its first reveal to the universe. There is another piece of the puzzle that needs to be satisfied for a synestia model to be the origin of the moon. In order to generate a synestia that reaches these conditions that match the chemistry of the moon, the system must have had greater angular momentum than we have today. That is, instead of having a 5-hour day when the moon formed, the Earth may have had something closer to a 3-hour day, or even slightly less. And so in order to get to the present day system with 24 hours, we have to transfer angular momentum away from the Earth-Moon system. And there are several dynamical mechanisms that can transfer angular momentum. It transfers angular momentum to the Earth-Sun system instead. And so we have been developing models that achieve transfer of angular momentum and can explain the non-zero inclination of the orbit of the moon. And so these are kind of crazy. You've got to imagine a number of things that may be different than what you thought. First is the tilt of the Earth doesn't have to be the same through Earth history, and there are mechanisms to change the tilt of the Earth, the obliquity of the Earth with respect to the ecliptic plane. And so if you start with the Earth tilted way over, that is the synestia tilted way over so that it's nearly spinning on its side, which is a probable outcome of a giant impact, form the moon with the system tilted over, the moon would be very inclined to the ecliptic plane. And then there's a dynamical transformation where the moon, Earth-Moon system, instead of the moon being dominated by precessing around the Earth's equator, is dominated by precessing around the sun's ecliptic. That's called the Laplace plane transition. What happens there is there's a resonance that raises the tilt of the Earth, but leaves the moon at a very inclined orbit. Then there are other dynamical effects that damp the inclination of the moon, but if you start very high up, it doesn't damp it all the way to zero. So we've been developing this model where making the moon out of a synestia that happened to be tilted very far over would naturally lead to the finite inclination that we have today. And so you should walk away with the idea in your head of, instead of thinking about the Earth with a disk that makes the moon. Think about the synestia and the moon forming within it as a different model, and that we are developing this to try and test ways of determining the exact formation of our moon, because there are still debates over which is the final answer for our moon. And we may require going back to the moon. At the end of this year, it will have been 50 years since men last went to the moon, and we brought back rock samples. NASA has a program called the Artemis program, which, if we are very optimistic, would send astronauts some few years from now. There are other countries also planning to send people back to the moon. There are multiple small lander missions planned for the far side of the moon to gather rocks that may have been excavated from the deep mantle of the moon by the largest crater on the moon on the far side. And that may help us with some of the chemistry questions that remain about the moon. Now, I was born 99 days after the last man left the moon, but some of you here remember the Apollo missions and watching the grainy videos of men leaping across the surface and the rovers. I have only been there in my imagination. I have imagined every stage from the origin of the moon to today, from that magma beginning to its freezing, the lava flows that covered part of the surface, fire fountains. The moon had a magnetic field. The moon still has secrets that we have not figured out. And so I hope I have told you a wonder story today about the origin of the Earth and the moon. I hope I will leave you with the words spoken by the last man on the moon as he left. It's important for all of us to gather and share in our wonder of science, even with war and suffering around us. We must celebrate the joys that we have here in our community, and let us leave here together with the same aspiration for peace for all mankind. Thank you.
Fantastic. And you're going to pick.
I'm going to pick.
Great talk, by the way. But can you give us some idea of the time scales we're talking about? When in the history of this, how long ago did this happen, and how long did it take to cool down into a recognizable?
Yes. So the giant impact phase of planet formation in our solar system was probably around the first 100 million years of the solar system. The precise date for unimpact origin of the moon is not precisely known, but let's say roughly in the 50 to 100 million year time frame. The time scales involved for a giant impact, the dynamical time to get back into some kind of stable shape is about a day or two. And then the cooling to actually grow the moon depends on the model. It could take months, it could take 100 years. But fast compared to recrystallizing the Earth. Going from the impact to a solid Earth again could take 1 million years. The magma moon can take longer to freeze because it forms this flotation crust that insulates it and keeps the inside warm. So it could take a couple 100 million years. It could take an order, we'll say tens of millions of years to freeze again. So those are the rough times. Our solar system is 4.568 billion years old. Yeah. Yes.
So great talk. Thank you. Very interesting. So when you talk about the chemical composition of the moon versus Earth, so are you talking about the surface chemical composition, like isotope composition, or like the composition deep in the mantle of the moon as well? So is it like uniformly distributed, or it's only located on the surface?
Right. So based on the samples that have been collected from the moon, we have samples of the highland crust, which is the lighter part of the lunar surface. That is this crust that floated in midway through crystallization of the magma ocean. And we have basalts that erupted and filled in the big craters on the near side. Those are the dark patches on the moon that make up the face or the rabbit in the moon. And then based on these samples, we reconstruct what we think the composition of the mantle is, based on understanding the phase relationships of partial melting. And so with these reconstructions, we can estimate the bulk composition of the moon and find that that is similar to our estimations of the bulk silicate part of the Earth. In terms of isotopes, with those same samples, we can measure a suite of isotopes in the lab, and in most isotopic systems, stable isotopic systems, the Earth and the moon are either identical within measurement precision or very, very close, and much closer between us than between any other bodies in the solar system. So those stable isotopes are thought to be representative of the bulk. Questions remain about the mantle because we have no direct mantle samples, which is why we're quite keen to return to this deep crater on the opposite side known as South Pole Aiken that is deep enough to have excavated deeper materials, and then we would learn more. Yeah. Yes?
Hi there. You briefly discussed exoplanets or mentioned exoplanets. Are there any ideas of how one might find evidence for synestia exoplanets?
Yes. So this would be wonderful. There's a couple of things that are possible. So most of our work on exoplanets has been around mature stars, and that's because most of our measurement techniques want the star to be as quiet as possible. So we're looking at older systems, they wouldn't be in the giant impact phase, they wouldn't be looking for synestias. Looking at younger stars, they're more variable, so it's harder to be convinced that you found a planet versus some other stellar activity. But there are predictions of what oddly shaped objects transiting in front of the star would look like now, so that if we see some odd passage in front, we would at least ask the question, could this be something different? But probably more promising is study of what are called extreme disks. And so we observe young disks around other stars that clearly have had things going on recently. Extreme debris production, evidence for rock vapor. They look like high velocity collisions happening within those disks. Most of what we found would be analogous to asteroids or outer solar system Kuiper belt type objects, not necessarily protoplanets colliding, but we're only a step away from that. And so there are people looking at these young active disks that we would have to be lucky to see something happen. And then it may be obscured by a lot of dust, but we'd know something different occurred.
What can we learn from studying the interactions between like spiral galaxies colliding, because they also go through like damping and other similar sort of phase transitions? I know they're not exactly the same, but I was wondering if there were applications from studying those.
So some of the dynamics of the disk formation are quite similar to galaxy mergers, and the instabilities that we see that in the disk have analogs that are happening at small scale. And so the people who focus primarily on the dynamical evolution are using the same physical models as in dominated by galaxies colliding. After that, we quickly run into systems that are dominated by the phase relationships of the materials. And that is because it's being buffered by the liquid vapor boundary, and that determines the physical structure of the gas disk and the thermodynamical buffers in the energy budgets. And so the initial distribution of material, I would say, is very gravity dominated and then quickly goes to a materials dominated system.
What about, can I go?
Yeah.
What about the moons of like the gas giants? Are they totally different? Because obviously the planets have a very different elemental composition.
Right. So, so I mentioned that our moon is quite different than other moons. In the outer solar system, the dwarf planets, most of the dwarf planets have moons. And so we think those are actually impact generated. But the gas giants have very small moons of a different composition. So these icy moons, we think that those formed in circumplanetary disks during the time period where the gas was still present in the solar nebula, and that the disks are the transition between feeding the planet's atmospheres from the solar nebula, so growing the hydrogen atmosphere of Jupiter and Saturn involve flow through a disk around those bodies. And we've actually observed Jupiter-like planet around another star with its own little accretion disk. And so that is sort of the context for forming the icy satellites.
Zero collision.
No, not a collision. Now, after the formation of moons in that way, there is a proposal for a collision onto Jupiter that would sort of shake up its core, because the spacecraft data we have from Jupiter indicates that the rocky, iron-rich center of Jupiter actually has a very fuzzy boundary with the hydrogen atmosphere. And one of the proposals is that there could have been a late collision after the gas disk went away that helped to mix up that core. They're still working on testing that model, but there could be collisions in the outer solar system as well, and there were certainly many smaller bodies that collided onto the big planets. Yes, yes.
And then Phobos and Deimos are just captured asteroids. Right?
No, nobody likes captured asteroids. It turns out that capturing asteroids is really hard, and it is a textbook sentence in most things, but they also probably formed in a disk, but a much smaller disk as well. And that one is really crazy because the one moon is falling inwards as well. And so there's a history of that disk where they may have broken up and remade moons multiple times. We're not looking necessarily at the original system.
So what's that big cone that came through our solar system that your Harvard colleague wants to be a spacecraft?
So we have observed interstellar objects traveling through our solar system. They are flyby events, right? The bodies that aren't bound, and some of them look weird and maybe made of things like nitrogen ice. There's a couple that have been definitively observed, and some calculation, extrapolation of how many are in the solar system at any one time, and there are many. Those are likely dynamical ejecta from other planetary systems during their giant planet formation. When giant planets migrate, they kick bodies out of that star system.
Hi, it was a really nice talk. I enjoyed it a lot. I was wondering if once you've made a synestia, what are the range of outcomes in terms of the number of bodies that can be produced?
Right.
Do you always have one planet, one moon, or is there a range of different outcomes, multiple moons?
So lots of moonlets are going to form inside this thing, and almost all of them are going to gas drag and spiral their way into the middle and be destroyed and become part of the planet that reforms. In order to form a moon that stays, it needs to form beyond what's known as the Roche limit. The Roche limit is the minimum distance where a body can remain intact to tidal forces from the main planet, and within that, tidal forces will break up the body. And so when you think of Saturn, Saturn's rings and the belt around Saturn, those are within the Roche limit. No large moons, because they all get broken up into the debris that make the rings. And so in our system, that distance is about 3 times the planet's radii. And so the moon, the primary moon, has to form further out. And it's a big moon. And so the dynamics of what was calculated in previous models with a bona fide disk is that usually 1 or 2 moons form, just because when the gravitational capture is heavily dominated by the largest bodies. So the natural outcome is 1 or 2 moons. In the dynamical evolution of our moon, 2 moons are not stable over the history of the solar system, and they'll either collide with the Earth, or one will get ejected. But especially with a moon as massive as ours, the dynamical timescale doesn't survive. So the trick is to grow a moon fast enough in a synestia and out far enough that it doesn't experience gas drag to bring it in to be lost. And that does place a real constraint on this model, and the physical modeling of that process has not been done yet robustly. We did a very simple first order numerical calculation, but much work needs to be done on it.